Dear students and participants on the course on railway engineering, today our focus will be on the provision of superelevation on the tracks. In the previous lecture, if you remember, we discussed about the circular curve. We talked about the radius, the degree of the curve, the watt sign, the relationships between the radius and the degree and between the watt sign and the degree. We also talked about the various elements which can be calculated for any of the circular curve. And then finally, there were different methods which were discussed which can be used to lay a circular curve in the field. So, there were some methods which were for smaller lengths, there were some methods which have been used by Indian Railways or being adopted by them. So, all of those have been discussed. So, depending on the situation, any of the methods can be utilized. Talking for today's discussion, we are going to discuss about the superelevation, which is also defined as Cant. We will look at the various definitions related to it. We will be talking about the equilibrium Cant and how this equilibrium Cant is calculated. What are the various limiting values related to Cant, and then we will solve few examples related to the superelevation or Cant. Let us start our discussion on Cant. Cant is what? Cant is a difference in height between the outer and the inner rail on the curve. We discussed in the previous lecture also. A curve is being provided. This is a curved track. This is outer rail and this one is inner rail. There is a centrifugal force which is acting outwards, and so as to counter that centrifugal force, what we do is we provide level difference between the outer rail and the inner rail. So, this level difference, if I talk in terms of the elevation condition with respect to outer and inner one, whatever is this being provided, this height is the Cant which we are talking, and in the terms of a rate it can be defined as C or it can be defined as E. Now, this inner rail is taken as a reference rail. So, this rail is being talked as reference rail, and it is also being talked as a gradient rail because with respect to this particular reference rail, the gradient has been set on the track so as to define the Cant, so as to define the value by which the outer side of the track is going to be raised so as to counteract the forces which are acting in the outward direction. Now, when we are talking about this particular value or a Cant, this is provided with respect to the movement on this track. There are number of trains which are moving, and from these trains they are moving at a speed of Vi. So, we cannot provide a Cant which keeps changing. If a train comes with a speed of V1, the Cant becomes C1. If the train comes with a speed V2, the Cant becomes C2. It is not that. This is a static value which is going to be provided on the track. So, what is that value for which it should be provided? And we discussed about it and we said there is a equilibrium speed for which the Cant is provided. So, whatever Cant which we are providing here is for equilibrium speed, and this equilibrium speed can be a weighted average of the various speed groups in which the number of trains are moving on that track. Now, when we discussed about this particular aspect in the case of the speeds on the tracks, the another thing comes up. Okay, we are providing for VE, but there are trains which are moving with a speed V1 which is greater than VE, or there are trains which are moving with a speed V2 which are less than VE. Now, for this VE, a Cant has been provided. So, if we say this is actual Cant, so there is going to be a different value of Cant here and there is a different value of Cant on the other side. Now, if these trains are coming and we are talking about this static value of the Cant being provided here as CA, then what will happen? Now, this VA, if it is increasing, it means the centrifugal force will be increasing, and this centrifugal force is increasing, but you have not provided that much rise. The rise could have been required like this. So, what we provided is this much. It may be required to provide this so as to cater for V1, or if you are talking about the trains which are moving at a lesser value, then the value which needs to be provided may be this much for V2. So, this two aspects, they create an issue. What are those? Let us talk about the first one is the Cant deficiency. Now, Cant deficiency occurs when the trains on the curve, they are moving at a speed higher than the equilibrium speed. That means we are talking about this first segment. They are moving at a speed higher than the equilibrium speed. That means the Cant which was required was this much, but what we provided was this much, and that is where there is a deficiency in the Cant which is provided. So, how we can find it out? The Cant deficiency is theoretical Cant for a high speed minus the actual Cant which is being provided, which is related to the equilibrium speed. So, you must have understood what we are talking here. Now, the another terminology is Cant axis. What it says? It says it occurs when the train runs on a curve at a slower speed than the equilibrium speed. Now, when this happens, that means we are talking about the another segment now, and this segment is here. That means, instead of the value which we have talked here as CA, what we are discussing is that only this much was required. So, if this is CA, this one is C1 and this one is C2. So, here C1 was greater than CA, and that caused the Cant deficiency here, and the another one is that CA is greater than C2, and this is causing the Cant axis here. So, CA is greater than the C2 value. Now, in these two cases, when we are talking about the deficiency and we are talking about the axis, what happens? In the case of deficiency, the overturning may be caused due to Cant deficiency. There is a more of the force which is acting in the outward direction, and we are not being able to counteract it. So, it means the train is trying to go towards the outer side, and it will create a problem. In the case when the trains are moving at the slower speeds, then what is happening? The force is not there for which the Cant is being provided, it is lesser than that. So, the train will start coming towards the inner side. There is a possibility of the derailment which may happen due to this Cant axis. That is where, considering these things, the limits needs to be provided. So, Cant axis is defined as actual Cant which is provided, which is CA related to the equilibrium speed, and the theoretical Cant for the slower speeds. Now, another terminology here is Cant gradient or Cant gradient deficiency. Now, what is this Cant gradient or Cant gradient deficiency? Now, we decided that we have to provide a value of CA. That means the CA will result in some height of the rails with respect to inner and outer rail. So, this is the total height which is to be provided, say HA, at the start of the curve. So, this is at the position of curve. And when we started at the straight section, it was simply both of the rails were having at the same elevation, or the levels were same at the surface of the rail head. So, this much height is to be attained. You cannot attain the height that just now the levels of the two rails are like this, and now at this point you are talking about the levels where all of a sudden a height comes in this form and the levels becomes this way. So, here the inner and outer rails were at the same level, but now inner is here and outer is here, and there is a sudden change. It will cause a further derailment of the train. So, what we do is this particular value is going to be provided in a smooth manner at a certain increase, uniform increase, and that is where the Cant gradient comes into play. So, this is an increase or decrease in the Cant or the deficiency of Cant in a given length of a transition. Now, when we are doing this type of a changeover, we are going from a straight section to the curved section. In between, the transition will be there. So, this transition length is going to be governed by the Cant deficiency. So, that means Cant deficiency becomes one of the point in terms of the calculation of the length of the transition curve. Then another is the rate of change of the Cant or Cant deficiency. At what particular rate it is changing. So, this is another value which we consider here, the rate at which the Cant deficiency increases while passing over the transition curve. Usually it is taken as 35 mm per second. For every second 35 mm rise can be, change can be there. So, this will also give you an idea. So, if you are talking in terms of the length, it is simpler that because the train is moving at a speed. So, if we consider that particular speed and then you use it with 35 mm value, this is mm per second. So, you will get the length. So, finally, what are the objectives of providing the Cant, or what are the objectives of providing a superelevation? Now, you can see on the diagram which is being shown on the right hand side, this is the inner rail and this is the outer rail, and there is a difference being provided in the levels of the inner rails and the outer rails, which is the superelevation or the Cant, and this gauge is being maintained between these two one, and because the pressure is there for the train to go this side or towards the outer side, another rail is being provided here to help it. So, these rails which are provided to assist it here, they are the check rails. So, what are the objectives here? Based on the discussion which we have done, the objectives can be made. Okay, so, what are those? First of all, neutralize the effect of the centrifugal force or the lateral force which is acting in the outward direction. So, we talked about it, and as soon as this is being done, there is going to be an equal or the better distribution of the wheel loads on both of the rails. We discussed about it. We said there is a P1 and the P2 load which is coming on the outer or inner rail. As far as possible, we should make them equal. So, the design should be such, and when we are talking about the equilibrium design, then this is what is going to be achieved. Then to provide a smooth track so that the passenger comfort can be improved, because when you are moving from a straight track to a curved track, there is a sudden application of a centrifugal force. So, if nothing is being provided in between here, the superelevation which is provided is not being done in a smooth manner. So, all of a sudden we will find that there is a jerk acting outwards. So, comfort is to be looked at, and that is where the superelevation has to be considered. And it also reduces the wear and tear of the rails as well as the rolling stock, because if not being provided, there will be either higher pressure on the outer rail or there will be higher pressure on the inner rail, and accordingly the wear and tear will be higher either on the outer rail or on the inner rail. So, let us talk about equilibrium Cant now. Now, to counteract the effect of the centrifugal force, the outer rail of the curve is elevated with respect to the inner rail by an amount equal to superelevation, which we have discussed. So, here what we can see is there is a change in the level here and as well as here. So, this is the amount of superelevation by which it is being raised. The same can be discussed with respect to the level here. Okay. So, this is the value of E. A state is reached when both the wheels exert equal pressure on the rail. Now, what we are doing, we are slowly and slowly increasing the height. The outer rail is going a bit up and up. So, when that is happening, one stage will come where the load which is coming on the outer rail and the inner rail, so this is outer and this is inner, that becomes more or less equal. At this point, whatever the Cant value is there, E value is there, or we can say C value is there, we can use any of those, that one is the equilibrium Cant. So, superelevation is this point is enough to make the resultant of the centrifugal force and the force exerted by the weight of the vehicle normal to the plane of the top surface of the rail. Now, what is that? So, this centrifugal force is acting here F outwards direction, because this is the outside, and this is the weight W which is acting vertically downwards. So, when we consider these two, then this resultant is going to be, so this is again the force P. So, this is the resultant, and this resultant becomes at 90° with the surface. So, this is a 90° angle, and this is what is being talked here. So, the situation has come when you have been raising the outer rail, the loads which are coming there as P1 and P2, they have become more or less equals to each other, and then at the same time the resultant that becomes normal to the level at which the rails are being placed. So, in this state of the equilibrium, the superelevation, that the difference between the level of the outer rail and the inner rail, is being termed as the equilibrium superelevation. Now, let us look how we can calculate the values. See, the force is the centrifugal force, we can also write as mass into acceleration. So, this is m is the mass and a is the acceleration. This is the radial acceleration which we are talking here, because it is a radial situation, it is on the curve, and this radial acceleration can be given by v square divided by r, where v is the speed with which the vehicle is moving on this curve and r is the radius of the curve. So, that means f becomes m into a, or it becomes m into v square divided by r, and we have discussed about this particular notation before also. Now, this m, that can also be written as terms of the weight, because we were talking about the weight acting vertically downwards here. So, it is w divided by g, and v square by r is already there. So, we have w divided by g into v square by r. Now, here this g is the acceleration due to gravity in meter per second square. Now, if we talk about this angle at which the resultant has been found, which is normal to the surface of the levels here. So, if suppose this angle is defined as alpha, so we can talk about tan alpha. So, if we talk about this tan alpha, this is the force divided by W. So, tan alpha here we can talk here, that is the centrifugal force divided by the weight of the train. So, this is on the basis of this geometry. Similarly, this alpha is also here by which the track is being raised. So, this angle is also alpha. So, when it is being raised, then what is happening? There is a difference in the height here. So, this is a difference in the height, and the distance on which this difference is occurring, this is the gauge. So, there is a gauge here between these two in the horizontal direction. So, considering this, what we get is difference in the height of the two rails and with respect to the gauge of the track. So, height difference is nothing but superelevation and gauge is g. So, we get tan alpha is equals to E divided by g, and similarly we are getting tan alpha is equals to centrifugal force divided by W. So, these are the two which we are getting. So, now if we take them together, so E divided by g is equals to F divided by W, and we put the value of F was W by g, which was m into V square by R. So, what we are getting is the value finally is E is equals to GV square divided by GR. So, depending on the units, then we can find it in meters or we can find it in any other unit. So, here the g is in meters, which is the speed of the train in meter per second, g is the acceleration due to gravity in meter per second square, and r is the radius of the curve in meters. So, if you change the units, then the superelevation can also be calculated in mm. Now, when we are putting the values here, so what we had is GV square divided by GR. So, it was GV square divided by GR. So, here this G is small. So, if we convert this into kilometers per hour and then using the value of G, what we can get is GV square divided by 127 R as another equation which can be used. So, here this is in mm, and this G is basically a dynamic gauge value, which is the gauge plus the width of the rail head. That means, we are talking from center of the rail to the another center of the another rail. So, that is what we are considering. So, gauge of the track and the width of rail head, and it is taken as 1750 mm for the broad gauge. So, if you put those values, so what we get further is 13.78 into V square by R. So, if the speed is given to you, if the radius is given to you, now you can calculate directly on the basis of this formula the value of E. Now, whatever value of E is calculated, say this value of E comes out to be 32.8 mm. What it says is that we should round it up to the next 5 mm. So, we can consider it as 35 mm. So, this is being rounded off. So, this is another thing you can remember. Let us look at one of the numerical here. The trains are running at a speed of 80 kilometers per hour. So, V is being given to you, capital V. It is a broad gauge. So, the G is known to us. Now, in this case dynamic value, so 1750 mm, and it is laid with a curve of 2 degrees. So, that will give you the radius R. So, degree and radius, they are being correlated as D is equals to 1750 divided by R. So, based on that, R is 1750 divided by D. So, what we get is 875 meter as the radius of the curve. Now, the equation is E is equals to GV square divided by 127 R. So, if we put the values here, G is 1750, V is 80 kilometers per hour, and R we have calculated as 875, what we get is 100.8 mm as the value of E. So, we can consider it even as 100 mm. Now, another thing is the equilibrium speed. So, Cant depends on the maximum speed of the fastest trains and the average speed of the goods train running on the track. So, we discussed about it when we have calculated the value of equilibrium speed VE in the previous lecture. The Cant should be such that the fast trains can run smoothly without discomfort to the passengers, and the slow trains can run safely without a fear of derailment due to excessive Cant. So, these two conditions needs to be taken into care. Now, this requires to arrive at an equilibrium speed as discussed in the previous lectures. We have already talked about that, and this equilibrium speed is decided by the chief engineer after taking into consideration certain elements. What are those elements? One is the maximum speed of the fast and the slow trains. So, we have V1 and V2. Proximity of the permanent speed restrictions in the routes, say junctions, stopping places, gradients, they all, we discussed about the various speed restriction schedules, where we talked about that is a condition or a 10 kilometer per hour, 20, 30 or 50 kilometer per hour condition. If you remember those, so that is what we are talking. So, we need to consider that also while we are talking about what should be the equilibrium speed on a section or a route. Now, entire section is divided into subsections. Now, the section which we are talking may be in kilometers, 50 kilometers, 100 kilometers. So, if that section is there, we cannot talk about the equilibrium speed for the whole section. It is better to discuss in terms of the subsections, see the condition of that particular subsection, and accordingly the speed should be set up. So, it may happen in some of the sections the speeds, equilibrium speeds are higher, where in some other sections where there are certain obstructions, there are certain proximities to stoppages and all, then the speeds can be lower. But if otherwise, if you consider whole of the section together, it will affect the efficiency of the network badly. This allows avoiding speed restrictions for limiting the Cant access for slow trains and Cant deficiency for fast trains throughout the track. These are some of the limiting values which are being given here. So, maximum degree in the case of broad gauge, if you remember, we discussed when we talking about the curves. So, it is 10 degrees. With respect to that, the minimum radius comes out to be 175 meters because of the relationship between that. So, D is equals to 1750 divided by R. So, maximum Cant, this is defined as 165 mm for A, B and C group routes. For D and E, it is defined as 140 mm. So, these values we need to remember, because when we are calculating the Cant values and the route is being defined by any of these classifications, if the value comes more than this, then it has to be restricted to either 165 or 140 mm. If it is less than this, there is no issue. Then maximum Cant deficiency is being considered as 75 mm for all broad gauge groups, that is A, B, C, D and E. In some special cases on A and B routes, it can be taken as 100 mm. So, you are talking about Shatabdi route, you are talking about a high speed route, you are talking about the Rajdhani routes, there is a possibility of taking the value as 100 mm. And Cant excess is taken as 75 mm. So, deficiency and excess, they are both same more or less as 75 mm, but in some cases Cant deficiency can be increased to 100. The maximum Cant gradient, it's 1 in 720, exceptional cases we can go to 1 in 360. The rate of change of Cant, there are desirable value and the maximum value. Desirable is 35 mm per second, but we can go to the highest value of 55 mm per second, specifically in cases where the high speed movements are there. So, these are various limiting values which we are going to use when we do the calculations. Then for speed up to 120 kilometer per hour, the maximum Cant is defined as 165, but if you go beyond 120, it is up to 160, it is 185 mm, and from 160 to 200 also it is being kept as 185 mm. There is a sort of a thumb rule here. The maximum Cant is 1/10 to 1/12 of the G. So, G here is a dynamic gauge. So, 1/10 to 1/12 of that G is the maximum value which is going to be there. Now, higher Cant deficiency means higher discomfort, higher unbalanced centrifugal force and extra force and lateral pressure on the outer rails. I think there is no need of elaborating on this particular point, because we have discussed about the Cant deficiency and what way it is going to impact is already being taken. Now, talking about the calculating the Cant and the permissible speed, calculate the Cant for the maximum sanctioned speed which is being sanctioned by the track engineer. So, considering that, so here this V will become Vm. So, we will use the formula Gv square divided by 127 R. Now, the formula will remain the same, the speeds are going to be different depending on what situation we are considering. So, G is gauge and R is the radius of the curve. Similarly, calculate the Cant for the slowest traffic. So, this slowest traffic, if you calculate the value Cs, again this V will change, it will be for the slow traffic. In that we add the Cant excess because it is lesser. So, we have to reach the actual Cant. So, this becomes actual Cant condition. Okay, so, Cs plus Ce, that is what we are considering here. Calculate the equilibrium speed Cp for that. So, if for calculating that we can use the formula and then check for the Cant deficiency. Now, you have got this Cp and the maximum value is also available to you, considering those which came from here. If you take a difference between the two, that is going to give you the Cant deficiency, and Cant deficiency limiting values we have seen. Cant deficiency can be 75 mm or 100 mm in the special conditions. So, if it is less than that, it is fine, but if it is going beyond, then you have to fix it up to the standard value. Then calculating the Cant and the permissible speed Vm, the lowest of the three values, that is Cm, Cs plus Ce and Cp are taken, and that will give you the permissible Cant Ca. Add the Cant deficiency to Ca and we calculate the value of Vm by using a formula which we have discussed under the discussion on the speeds on tracks, that is 0.27 in under root of Ca plus Cd into R. On sections where, like the suburban rail sections where all the trains are running at about the same maximum permissible speeds, the Cant shall be provided for that particular speed itself. So, there is no requirement of calculating all the three cases and doing that way. Let us look at one of the numerical here. So, it is a broad gauge, transition is being provided, curve is of 2 degrees, maximum sanctioned speed is 110. And there is an equilibrium superelevation is to be calculated for a speed of 80 kilometers per hour, and the booked speed of the goods train, that means the slower speed is also being given, which is 50 kilometers per hour. So, you have to calculate superelevation as well as the maximum permissible speed on this track. So, we have given the degree of the curve. So, from degree of the curve we can calculate the radius. So, it comes out to be 1750 divided by degree. So, 875 meter is the radius. Now, superelevation for the equilibrium speed, say E1, the equilibrium speed was given as 80 kilometers per hour, 875 we just calculated. Using the equation, what we get is 100.8 mm. Maximum permissible speed was defined as 110 kilometers per hour, again using the same formula, what we get is 190.6 mm. So, this is maximum permissible speed. So, the Cant deficiency which comes out here with respect to the equilibrium speed is 190.6 minus 100.8, that is 89.8 mm. Considering that this is a high speed track we are talking, so we can go up to a value of 100 mm as a Cant deficiency. So, it is okay, but if say we are not considering this and we are going only up to 75 mm, then the value has to be restricted to 75 mm. Then superelevation for the booked speed of the goods train, which was lower, which was 50 kilometers per hour. So, for that what we get is 39.4 as the superelevation or the Cant to be provided. But what we are providing? What we are providing is we have got as an equilibrium value of 100.8 mm. So, there is a Cant excess. 100.8 we are providing and 39.4 is required for the slow train. So, the value is 61.4 mm and this 61.4 mm is less than 75 mm, hence this is okay. Now, once we have got this values, so what we can find out the safe speed on the track. So, it is CA plus CD. CA we calculated as 100.8 and CD is being calculated here as 89.8. So, this 89.8 is being taken. We are putting the values here. What we get is 110.26 kilometer per hour. So, this is a safe speed. So, the maximum sanctioned speed was given as 110. The safe speed which we have calculated is 110.1. There is no speed restriction due to a transition length because the transition has been provided in a perfect manner, is what is being defined in the numerical itself. So, considering the three cases, whatever is the value which we are going to get here is they are more or less same. So, we provide 110 kilometers per hour with the equilibrium Cant of 100.8 mm and this 100.8 mm can be just rounded to 100 mm, as we said it is rounded to 5 mm multiples. This same numerical can also be solved in a different manner. That is what we are going to look at here. The same data is being used. There is no change in the data. 2-degree curve, 110 kilometers per hour of the maximum sanctioned speed. Equilibrium speed is 80 and for the goods train it is 50 kilometers per hour. So, we first calculated the radius, it is 875 meters, and then with respect to that radius we have calculated the equilibrium Cant. So, as we did previously it was 100.8 mm. Now, Cant for the maximum permissible speed. So, it is 110 kilometers per hour the speed being given. So, it we calculated as 190.6 and then we also calculated the Cant for the booked speed of trains which was 50 kilometers per hour. So, for 50 kilometers per hour we have got a value of 39.4 mm. Now, suppose we start from here, this is 39.4 mm and the Cant excess which is allowed is 75 mm. If we add that 75 mm, what we get is 114.4. So, we have one value here, there is another value here and now we got a third value which is basically the Cant for the goods train plus C axis. If you remember we discussed about it that this is how we can find out the equilibrium Cant. So, when we have got the three values we take the lowest of the three and the lowest of the three is 100.8 mm being rounded to 100 mm. So, this is the value which we can consider now. Now, on this the Cant deficiency can be added. So, if we add that Cant deficiency 100 plus 75, what we get is 110.1 kilometer per hour. That means the permissible speed can be 110 kilometers per hour with a super elevation of 100 mm. So, this is the another way the same numerical can be solved. Let us look at another numerical here. This is a transition curve of 3 degrees, maximum sanctioned speed again 110, equilibrium speed 80, booked speed of goods train 50. So, these values are more or less same, only change is in terms of the degree of the curve. With respect to this degree of the curve, the radius of the track is going to change and now it comes out to be 583.3 meters. Now, this 583.3 meters we will taking forward. So, we have the equilibrium speed with respect to 80 kilometers per hour. So, what we get 151.2 mm. Previously for that was a 1 degree curve we were getting 100.8 mm. For a maximum speed, sanctioned speed of 110, but because here the radius has changed, what we are getting is the Cant for the maximum sanctioned speed is 285.5, a big value. So, the Cant deficiency is the difference between the two values. So, the difference between the two values comes out to be 134.6 mm. So, even if it is a high speed track, we cannot go beyond 100 mm, that is the limit. So, that means this 134.6 has to be restricted to 100 mm, and this is what we have done here. Now, actual Cant which will be there, so we have restricted the deficiency to 100. So, we are going back for the high speed we calculated 285.5. So, this is 285.5 here. So, 285.5 minus 100 is 185.5 mm. Again we have discussed that the Cant in the case of group A, B and C can be 165 mm maximum. So, if we consider that 165 mm, so this value is again being restricted. So, we restrict it and then we will be using this value now. In terms of the goods train, which is the slower speed of 50 kilometers per hour, what we are getting is 59 mm here. So, the actual value is being restricted to 165. What we are getting for goods train on the slow side is 59. So, the difference between the two is 106 mm. Again, Cant axis cannot be more than 75 mm. That is what we have discussed in the terms of the permissible limits. So, when you are talking about this 75 mm, now let us take this 75 mm and use it with the requirement of a Cant for the goods train, we will get 134 or 135 mm as the value. So, this is another value which we have. So, we have value of 135, we have value of 165, we have value of the highest one that was of 285. So, considering the minimum of the three, the value comes out to be 135 mm. Now, we will use this value of 135 and the Cant deficiency of say 100. If we are considering that with the radius of 583.3, we are getting the safe speed as 99.6 kilometers per hour. We can round it off to 100 kilometers per hour. So, that is how we can solve this type of a numerical. So, in this particular numerical you have seen, so we have used the restrictions in almost around 3 locations with respect to deficiency, with respect to access, with respect to actual Cant which needs to be provided. So, you need to be very careful while solving such type of numericals. With this we close our discussion now. So, today we discussed about the Cant or the superelevation, we talked about the various definitions which are related with them. Then we discussed how the equilibrium Cant can be calculated or equilibrium speed can be used. We also talked about the various limiting values related to the Cant, related to the Cant deficiency, Cant access, the rate of Cant on which it can be provided, all those things as well as the Cant gradient. And then finally, we have solved some of the numericals to see how these values can be applied so as to calculate the superelevation to be provided on a track as well as the maximum speed which can be there on that particular track. With this, we close it now. Thank you and bye.